They do like patient speech it's something we need. I don't think it's like. Yeah, there wasn't a whole lot of application. It was a hard. You can't like actually do it. And that's so you're I killed like relatively. I struggled through the whole class. And maybe we have like 20 so between that and the 25 extra credits, yeah, whatever, 100% on that. Yeah, I didn't think. I knew people I took at the summit. I talked to someone who was literally 6 hours. And still took it 2 nights. 6 hours for all the homework. And he's not like he's not super brilliant. Right. Well, I mean, most of it's work anyway. 6 hours. I was like, fourth of homework. Yeah. There was a period from like September 1st to I think September 20th where I spent every day. The only reason I stopped was because you didn't. I filled literally 3 notebooks. Practice problems. Oh yeah. Both sides of every page. Luckily, really? That makes me feel good afterwards.
All right, let's get started. First of all, I've had 0 feedback. You guys all received my email from last night, right? Okay. So the mailing list works because part of the mailing bounced, but I had no other feedback, so good. Any questions on the logistics of the course? Any at all? So the homeworks, we'll have 5 of them. They're coming, but I can't assign the homeworks before I've taught you something. So the first homework, I'll give it to you by the end of next week, actually. And then it'll be due in 2.5 weeks. And then afterwards, there'll be a 3-week delay for each of the homeworks going forward. And the quizzes also will start, but as I've emphasized so many times, they're completely informal. So the quizzes will be, so based upon today's lecture, it'll be a very simple quiz that you can take before next week. Okay. What I think I told you last time, and what I had really planned to do, and what I've done in the past, is to start the course by talking about molecular computing, which is a big theme. But this year, for no particular reason, just to mix things up, I'm going to start with a different topic, which is a circuit-based topic. But as you'll see, there'll be a relationship between some of the mathematics, and there'll be a little bit of math that I'll talk about today. It shouldn't scare anybody. But the math that we use here and the framework that we use here for this circuit-based idea and molecular computing that we introduce later on. But this will be one of the themes of the course, which is circuits that compute in terms of probabilities. As I'm teaching this for the non-electrical engineering students in the audience, I'll really try today and in future lectures to give you everything that you need to know. But be forewarned that I'll be talking about logic gates, and I'll be talking about constructs with logic gates. For those of you who don't have the background, just let me help you understand, or just suspend your disbelief a little bit to try to look for the big picture before the details, and then the details perhaps will come. Okay, so let's start. So I had some of you, actually quite a few of you, in an intro to digital design. We start that course by talking about number systems. And it's actually either amusing or irritating to the students because we discuss how to count. We literally discuss how to count first in base 10 and then how to count in binary. And most people, including myself, discover that we either forgot how to do basic arithmetic or we never really understood it in the first place. I won't be talking about that so much in this course, but I will introduce just for a few minutes the concept of a positional encoding of information to compare and contrast it to a different type of encoding. Already I'm lapsing into jargon. So, Scott, what do I mean by an encoding? That's jargonish, right?
Something that takes some information and views it in a different light or something.
Very good. So we're going to be talking about numbers and circuits that operate on numbers. And what I mean by an encoding, which is jargon, is how we represent that number. So that might not even be clear, except when you consider that a computer system, even non-electrical engineers will know, that it represents things as zeros and ones. So that's already an encoding. Okay. So since I had some of you in 2301, Michelle, what is a positional encoding?
Sorry, I don't know.
So, and you got an A in the class. Sorry.
Oh, is it when you like multiply it by 2
Yeah.
or 0?
Right. So what I mean by a positional encoding is the encoding that we're accustomed to. This is going to be, I'm going to use a couple of mascots. I'm going to use the caveman mascot in a moment. You'll understand why, but for the time being, I'm using this mascot. So a positional encoding of numbers is the one that we're all accustomed to. It's one in which we represent the number as multiples of multiples, so 7, 5, or 7, of powers of a base. In this case, base 10, we're humans. Why base 10? Because we have 10 digits. So, but the point that I'm really trying to emphasize, because I'll compare and contrast it to another type of encoding, is the positional part. The positional part means that when we have the number, the order in which we read the number, in this case 757, matters, because the position determines what power of the base we're multiplying it by. So it's positional. So what are some what are some other number systems? Pardon me? Hex. So it's a positional system with base 16. Binary is base 2. What are some other number systems? Octal. What are some other that aren't exactly the same but with a different base?
Base 7?
But can anyone think of one? Mackenzie?
Like tally marks?
Tally marks? Yeah, we'll get to that. But what about the Roman numerals? So Roman numerals are a positional system, but with messed up rules that make things complicated. Okay, so that's the positional encoding. Computers operate on a positional encoding that, in fact, is, for the non-computer engineers, exactly the same in every sense, except that the base that we use is 2 instead of 10. But it's positional. So a number in binary, 10, 1011, represents multiples, so either 0 or 1, times a power of the base, so a power of 2. So this is in base 10, or however we choose to represent on the right-hand side. That's how the number on the left-hand side should be read or understood. Okay, so, but Mackenzie mentioned an interesting method, a tally system. So what would be a tally system?
Well, it's just like a non-positional system.
Yeah.
It's just tally marks, but you're still using it to count.
Yeah, because that's going to be very close to what I'll be discussing for most of the lecture. In fact, maybe exactly what I'll be discussing. We'll get there in a moment. Okay, but, okay, so why a positional system? It was Seamus? Seamus, a nice Irish name, and remind me? Anthony and Jesse Anthony Seamus, right? Okay, so Jesse, why do we use a positional system?
Because we read in a certain direction.
Yeah.
And it's easy to just do
Yeah.
things with the direction.
Yeah, it has a lot of advantages, but the one that I'm going to emphasize here is that it's compact. So we can represent increasingly large numbers with a minimum of scratch marks on a piece of paper or a minimum of information. And this is intuitive, given the base. 10, going up by powers of 10 means we quickly increase the magnitude of the number, or stated differently, for using just a handful of symbols ordered, we can represent large numbers or we can represent many numbers. So it's a very compact system. And the number of symbols that you use, so if we choose decimal, where we have the symbol 0 through 9, if we have binary, obviously affects the range of numbers that we can represent. But perhaps counterintuitively, if you've never seen binary before, even though we're just using two stupid symbols, 0 and 1, powers of 2 increase rapidly. Not as rapidly as powers of 10, but they increase rapidly. So it actually doesn't take very many binary digits before you can represent numbers in the billions, trillions, or zillions. So a positional number system makes sense, and I think that's why we use it. That and the fact that the arithmetic on it makes sense. All right. But then the argument that I'm going to try to make in a moment is that by some measures, operating on a positional system is complicated. So some opinions on this. So Jason, why is, maybe it isn't to you, but why is operating on a positional system complicated?
I guess I don't think that it is. Perhaps if you're looking at something after a decimal, maybe.
Yeah. Because I'm trying to kind of, because we all, I think, feel that it's not complicated because we've learned how to do it. Yeah, Jordan?
Last semester in the Intro to Digital Design, you showed us how what the algorithm is for carrying a number.
Yeah. So I'm not going to go through any of that in this lecture, but if we have a number like 757 times 36, so this multiplication, to do it, what we have to do is we have to do a bit of work. So we have to do repeated multiplications, and then we have to do a sequence of additions. So we do repeated multiplications, and then we do a sequence of additions to arrive at it. So it's subjective or not to say whether this is complicated or not. But the complexity, I would argue, is that given such a number, before we can do anything with it, we have to decode it. So Jason, what do I mean by decoding it? Scott. I knew that.
Decode it, we have to take it from that other light over there and make it make sense in our brains.
Yeah? Okay, so as humans we have to decode it, but what in terms of, because this is going to be a very, in contrast to the first lecture where I was talking about brains and neurons, this is going to be a very computer-centric lecture. So the computer, what does it have to do? Why does it have to do the decoding? What do I mean by decoding?
You mean that the computer has to make sense of it, meaning it has to know what ones and zeros and where all those ones and zeros go?
Yeah, but it has to do more than that. What it has to do is, because it's a positional system, it has to assign a weighting to each digit according to its position. So conceptually, if we want to do multiplication in decimal or binary, what we have to do is, I'm using a metaphor here, but we have to blow up the number partially. So here, when we're doing the multiplication, we have to expand the number that we're multiplying according to its weighting. So we have to do the expanding. And then when we do the repeated additions for multiplication, we re-encode it, as it were. So we pack it back in. So the positional number system, because it's positional, and we have to weight each digit according to its position, we have to do work on it to operate on it, because we have to somehow explode it or assign a weighting according to its position, operate on it, and then re-encode it. Okay, so I'm going to go great length to set up what I think will be the alternate system. And so for the alternate system, well, I won't go into details here, but for those of you who are electrical or computer engineers, if you think for a moment of what it takes to build a multiplier. So students in introductory courses in computer engineering learn how to build a circuit that multiplies two numbers in binary. To do that, we essentially implement the same algorithm we would do by hand. Let me just go through an example for the non-computer engineers. Okay, so Michelle, help me multiply this number. How would you do it?
Since it's a 1, we just
So I'm immediately doing operations in binary, which some of you may not have seen.
So you multiply 1 times 1,
Yeah,
and then go backwards, all of them.
sure.
And then you add a 0 and
Yeah.
another next line.
Okay. So I ask you to tell me how to do it, and then I proceeded to do it myself, which is rude. But the point is, even if you've never seen operations in binary are conceptually the same as operations in base 10 that you know. You just operate in a different base. But the rules of how to do multiplication are going to be the same. So we're going to do multiplication as a repeated series of addition with each step of the addition shifted, which is in base 10 equivalent to a multiplication by base 10, in base 2 equivalent to a multiplication by base 2. But let me just show you how we do multiplication to demystify it. So pretend it was decimal. If it was decimal, you do this number here, so this is multiplication, this number here times this number here. What is 1 times a number? Well, it's the same in binaries as in decimal. 1 times a number is just that number. So that's simple. Just write it down. So 1 times a number is just that number. Then go to the next step. What is 0 times a number? 0 times a number, like in decimal, is just 0. So write down, if you want, a sequence of zeros. What is 1 times a number? Well, it's just that number. And notice here that I am doing the shifting. And now we have to add. The addition part is something that you have to learn how to do or understand how to do in a different base. But it's the same as in decimal. Here it's 1 plus, I guess we can pad this with zeros. 1 plus 0, 0 is just 1. 1 plus 0, 0 is 1. 0, 0, 1, 0, 0, 1, 1, 0, 1. It just so happened in this case that it was as simple as shown here. All right, but this is how we multiply numbers in binary, just like we multiply them in decimal. And to build a circuit that does this, we build it out of logic gates. Logic gates are gates that operate on zeros and ones. And we essentially implement exactly this algorithm or this procedure as a circuit shown here. But the point that I'm trying to make is that doing this is work. It's work in the sense that we require to multiply 2 3-bit numbers. So if we have binary numbers that have just 3 bits, to multiply them we need about 30 logic gates. Okay. All right, having set up this task of multiplication as a complicated task, can anyone suggest a much simpler way to do multiplication? Shifting. Who said that? I'm sorry, there's a voice and I can't localize it. Who's saying that? Now they're quiet. Oh, ripple carry adder. A ripple carry adder, okay. So that would implement the addition part. But how could we do? Okay, let me now turn to my mascot. Oh, actually, where's my mascot? There we go. So, my mascot. Suppose that we were cave people. And suppose that arithmetic hadn't been invented yet. There probably was a time when arithmetic hadn't been invented yet. And that probably wasn't so long ago. Imagine that you're a cave person, and you want to represent a number, but a positional system hadn't been invented yet. Then how might you do it? So Chris, what might you do? And
I hadn't invented multiplication, how would I do it?
well, and you hadn't even, the positional system hadn't been invented. So don't reinvent the positional system, but really think like a caveman. How would you represent number?
My fingers.
Uh-huh. But suppose you needed more than 10.
I get a stick and count as just one more than 10.
So, okay, but suppose that all you had was rock.
Can't break the rock?
But suppose you're next to a dry riverbed, and there's as many rocks as you want. How would you represent number?
One number could be one rock.
Okay, that's very good. And so this is exactly where I'm going. This is probably how you would represent numbers. I think that's what Mackenzie was saying, a tally system, where basically, is this what a tally system is? Yeah. So basically, if I want to represent a number like 35, I go and I collect 35 rocks. I make a pile of rocks. I think this is probably how cave people represented numbers. So the larger the pile, the greater the number. This sounds pretty good. Okay. So that was first stupid caveman. The slightly more intelligent caveman is going to choose a different method. I'm trying to build this up in your heads for you to anticipate where I'm going. So one problem with that is that to represent really big numbers, you need really big piles. So suppose that in the dry riverbed next to where we live, there are rocks of two colors. There is white and there's black rocks. Okay, now how could you represent numbers given white and black rocks? Chris, what would you do?
Just like we do in binary.
Yeah, but we haven't invented the positional system, or we're not going to.
One's worth 10, one's worth 1.
Oh, no, that's positional. Or, no, I guess it's not. But we're not going to do that. What's your name?
Ryan.
Ryan.
You just have one rock be 2 rocks, basically.
So
It's still positional.
it's not positional, but that's not where I'm going. So where I'm going, let me set this up a little bit further. There's going to be a bucket. And suppose that the cave people want to use rocks as currency. There's going to be a bucket. Inside the bucket, you can put both black rocks and white rocks. And you want to represent numbers. How might you choose to represent numbers? Ryan.
With some rocks being worth more than other rocks.
So not really so much one being worth more than the other. So Jack, where am I going with this? Usually people get where I'm going with this. I am not setting it up right.
Maybe like one color of rock could represent one thing, and the other color of rock represents like a multiplier.
You guys are all being smart cave people. Don't be smart. Okay, so where I'm going with this is suppose that we choose to represent the number as the fraction of black versus white. So this way, our buckets will always be the same size. So you have cave people, they just walk around with buckets. The bucket's always the same size. It's just the value that's in the bucket is the fraction of black versus white. The more black, the higher the number. So what range of numbers could you represent then?
All of them 0 to 1 would be the upper limit.
Oh, okay, and so suppose the upper limit is 1 and the lower limit is 0. So you can represent numbers in the range 0 to 1 by buckets, where the bucket is always the same size, and you just choose to represent it by the fraction of black versus white rocks in your bucket. This would seem like a pretty good number system. It could even be a system of currency among cave people. Is it making sense? Okay, now here comes the challenge. Suppose that you're a cave person, and now you want to do a task like multiplication. So you have buckets that represent numbers, and you want to multiply 2 numbers. What will you do? Think about this for a second. Ryan, what would you do? So should I draw this out?
Probably something like what, I don't know, we do with numbers. I'd put one black rock in the second bucket every time I fill up the other bucket of white rocks, something like that.
Yeah, close. But, or maybe not so close. Because I think if I set this up properly, some of you will get this. Suppose that, to be concrete, I've got 2 buckets, and what I want to do is multiply them and get the result in the 3rd bucket. So in this bucket, I might have a half, so I might have half black. I guess we're going to use black and green. And in this bucket, we might have a quarter black. So, and imagine the numbers. So here we don't have necessarily 8 rocks in a bucket. Perhaps we have quite a bit more than 8. How could you multiply these 2 numbers? And do this in general, if you're a cave person. What is the algorithm you would choose to assemble the new bucket? You'll have to make an assumption here. And the assumption was on the title slide that I quickly glossed over. We'll need a concept here that we haven't introduced otherwise. Where am I going with this? Someone can guess. Yes, your name is Seamus.
Could you take a black rock, or take a rock from one bucket?
That's good.
Keep other bucket until you get the same color and put all those in the other bucket?
Well, one problem with that is that even though we're not going to fuss about the weight, what we want is to, as our system of currency, to always have buckets that have roughly the same weight. So using that method, I think we might end up with a whole lot more rocks in here. Mackenzie?
So you have an and grade on the screen, so I'm guessing it would work like that. So you'd randomly pick a rock from each bucket.
Very good.
If they're both black,
Very
then
good.
put a black one in the
Very good.
other bucket.
So let me repeat what Mackenzie said and then explain to us why this, you're going to have to make an assumption here, but explain to us in a second why this works. So Mackenzie's suggestion was, if you're a cave person and you're at the market, usually when I give this lecture, I start talking like cave person. So you cave person, you at market, you want multiply two number. What you do? Okay, I'll stop with that. So you want to multiply two numbers. Here's the algorithm. You've got the two buckets. You want to multiply the numbers. Reach into both buckets. Pull out rocks. If both rocks are black, put a black rock in here. If either or both rocks are white, then put a white rock in here. Does that make sense? Black is going to be, it's the fraction of black versus white. Reach into both these buckets, pull out two rocks, look at them. If they're both black, then put a black rock in here. If either or both are white, then put a white rock. So why does that implement multiplication, Mackenzie? Or why could it? You have to make an assumption here. So what does the cave person have to do? I think if he just does that, I have to make an assumption about the buckets.
I mean, they have to be big buckets.
Big buckets, and what else do you have to do? You have to shake the buckets.
Yeah,
So-
it has to be random.
It has to be randomized. So the assumption is that we have big buckets, relatively big buckets, and that we shake up the buckets so that the black and white are mixed. So in other words, when we reach into each bucket and take a rock from each, the probability of getting a black in that grab will be equal to the fraction of black versus white. So that's a realistic assumption for large buckets, right? That you've got a large bucket. What is the probability of getting a black rock versus a white rock? Well, it's going to be equal to the fraction of black versus white if the rocks are all the same and the buckets are well mixed. But that's the only assumption you need. And you make that assumption, then this algorithm works. So why, Mackenzie?
I guess I don't know exactly why, but isn't it just like with probability?
It's exactly with probability. So tell us about the probability rules here. So what assumptions are we making in terms of probabilities, and why is this correct? Just because there's going to be a crucial term that we need here. So the probability of two events happening, and what is the jargon that comes next? Yeah.
So the goal of independent is
Independent.
the multiplication rule, chain rule, whatever.
Right. So recall, and this is just about the only probability we're going to invoke here, but recall from your elementary probability theory that the probability of two events happening, I'm not even stating this properly. The probability of getting two heads in two flips of a coin is going to be equal to the product of getting a head in each flip, provided that the flipping of the coin is independent and random. So in this case, provided that reaching into each bucket is random and independent, then what is the probability of getting two rocks? It's going to be equal to the probability of getting a rock in this grab times the probability of getting a rock in this grab. So the result is going to be here, if we call this A and we call this B, what is the probability of putting a black rock in here? C, well, it's going to be equal to probability of putting a black rock in here is going to be equal to 1/2 times a quarter. So if we do this right, it's going to be equal to 1/8. So here we will get a bucket that has 1/8 black rocks versus white rocks. Is everybody buying this? Okay. So as Mackenzie spotted, the cave person is actually going to use logic gates to perform this operation. So how? Well, The number that the cave person will represent will be simply the fraction of ones versus zeros, 1 being a black rock, 0 being a white rock. And the logic operation that we're going to use is going to be an AND operation. So someone, Scott, remind us, what is an AND operation?
An AND operation only gives you 1 if both inputs are 1.
Yeah. So for the non-computer engineers, that's all you have to know about an AND gate. It's simply a gate that produces a 1 if both inputs are 1. So it's like the verbal connective or the logical connective of, if you've taken courses in this, it's like a conjunction, or it's like the AND operation. It's like the verbal AND. Okay. So meaning here, for a given bit that we produce at the output, we produce that bit of 1 if we get 2 ones on the input. If either input is a 0, we get a 0, or they're both 0. So my argument is that this AND gate now performs multiplication. Why is this exciting? Well, as I tried to set up on the previous slides, doing multiplication the ordinary way with logic is actually complex. We have to implement the algorithm where we do a repeated series of multiplications and additions and then assemble the full result, which is a lot of work. Here we're going to do this. We're going to do a complicated operation like multiplication with a single gate. So can anyone see? So where am I going with this? Jason, any ideas? So we can do multiplication. At this point, you should be a little bit underwhelmed. You might say, OK, so you can do multiplication. But
That's where I'm at.
yeah. But
You can do a multiplication between 0 and 1, but you're still going to need something to count it afterwards in order to fully implement
yeah.
and get your answer.
Well, so the paradigm I'm going to talk about for the rest of this lecture is counting it or not counting it. We're going to build a full computer system that operates on random bit streams, randomized bit streams. Randomized bit streams will be the way that the entire computation flows through the computer system. The traditional way is to take your number and represent it in the positional binary system and then build your full computer system to operate on binary. And instead, we're going to build a computer system that begins with the numbers as randomized bit streams, operates on them as randomized bit streams, and produces the output in terms of randomized bit streams. But continue with your question or your thought, Jason. So you have to do something with it. What do you have to do with it? Why is that complicated, or might that be inconvenient?
Well, I'm just thinking it's because the multiplication before started with AND gates also on the positional one,
Mm-hmm.
but you still had to process it afterwards. So I guess I'm not sure how this one, to get your actual number, you're still going to have to count ones versus zeros.
That's true. But to get your actual number in binary, you have to do something too. So the question is, no, but it's a good question. I appreciate it. What do you mean by actual number?
So your result, to find out what your
Yeah.
result of the multiplication is.
But who needs to find the value of the number? Is it you who's examining how the computer system behaves? OK. Let me instead describe, because I'm going, as I always do, rather slowly. Let me try to position how the paradigm might work, and because I have to show you much more before you get excited about this paradigm. All right, so how the paradigm might work. Consider an end-to-end computer system. Consider a very simple computer system like something like a microcontroller. A microcontroller might be the sort of circuitry that you find in a thermostat on the wall. So what does it do? What does the thermostat do? Well, the thermostat takes an output of a sensor, which is a circuit that measures temperature. That circuit converts temperature into a voltage, typically. The voltage then is converted by a special, it's often called an A to D circuit, so it goes from the analog voltage value to a digital value. There's circuitry that takes the temperature reading in the form of voltage and converts it into a number. That's the A to D circuitry. Then that number is the input to your thermostat, and your thermostat does some calculations. In the old days, it would just turn on or off a heater. Nowadays, apparently, there's all these commercials about intelligent thermostats. I'm rather unimpressed by that, because those of you who have taken courses in computer engineering, you can probably assume that for you to build this super intelligent thermostat wouldn't be that difficult. So you guys have seen the commercials for, it's the Nest. Google paid a lot of money for this company that builds intelligent thermostats. As far as I can tell, what it does is you can control it from your different iDevices. So you can turn it on and off from the iDevices. And then it has memory. So it remembers what time of day you turned it on or off. Probably pretty easy to implement that. Okay, but the thermostat then is a device that takes a temperature reading, converts it to a voltage, and takes the voltage, converts it to a number. The number then is the input. It does some calculations, and based upon the calculations, it produces an output, and the output activates a heater, let's say. The point is that that number that goes in all existing computer systems is encoded in this positional binary system. But suppose that it wasn't. Suppose that the input number would be simply represented as a stream of bits, where you have the fraction of 1 versus 0 being the number that's represented. This is simple and intuitive. So here, the voltage, which represents the temperature, is simply the fraction of 1s versus 0s. This goes in. Then this goes into your circuit that does the calculations that it's supposed to do. It figures out, based upon the calculations, what sort of output value it should produce. And the output value that it produces it first in a string of 0s and 1s, because that's all it operates on. And then that string of 0s and 1s goes to the actuator that, based upon the fraction of 1s versus 0s, turns on the heater to the right level. So just to answer your question, Jason, we'll just leave it in this fractional form, or this, I call it random bitstream form, throughout. We'll never convert it. Yeah, okay. But still, I think you're underwhelmed because you're thinking, okay, so you can do multiplication. Well, how can we do other operations? And by the way, while I'm on this slide, just let me take the time to explain to you formally what's going on. So here, I'll use lowercase letters to represent probability values. I'll use uppercase letters to represent lines in the circuit, or wires. So the output probability lowercase c is going to be the probability of getting a 1 at the output. That's going to be equal to the probability of simultaneously getting 2 1s on the inputs. So getting an a equals 1 and a b equals 1. Now comes the assumption that the 0s and 1s on the input bit streams are random and independent. If they are, then the probability of the joint probability is equal to the product of the individual probabilities. So the probability of getting a 1 on A times the probability of getting a 1 on B, which in the lowercase symbols are just A and B. So we have C equals A times B. That's how this implements multiplication. All right. So that was all boring. Now, how do we do addition? Any ideas? Ryan, how would you do addition? So we know how to multiply. I'm going to explain to you how to do general computations. Doing addition would be useful too. And what's the immediate problem?
I mean, you have limited length bit streams.
But there's another even more basic problem. Yeah, Jesse?
Couldn't you do something like when we used and here, probabilistic method, using an OR method?
An OR method. That's immediately intuitive. It doesn't work. So recall from probabilities that if you just think about it for a moment. If you have 2 random events and you take the logical OR of them, you don't get the sum. What do you get? You get the union. That's not quite the sum. And more specifically, in terms of caveman currencies here, suppose that I had 3/4 and 3/4. Well, taking the OR of this is not going to give you the sum, which is greater than 1, so there's a problem here. The problem is you can't add probabilities. It's not even mathematically correct to add probabilities because you can get a number that's greater than 1. So I've wasted your time now. I've showed you a construct that only works for multiplication, and there's nowhere else to go. That's not the case. So where are we going to go with this? Any ideas? Sorry, you can see my teaching style is I prod you guys pretty hard to anticipate where I'm going because it gets your minds going. So Chris, what?
I don't have anything in this one.
Yeah. Yes.
So is that, it might not be mathematically correct, but can you just throw the two buckets together and then throw half the rocks?
Uh-huh. But suppose that, and I think that's exactly right. So then, because what I had in mind was take half the rocks, and just throw them into the bucket. That's exactly what you said, right? So throw them together and only keep half. So that is implementing a form of addition, but what is the formula that it's implementing? If you had to write this down. I think I've got this on the next screen. So there is multiplication. I'll let you guys stare at this for a second. I had too much caffeine. I'll be right back. Okay, so first of all, I should accelerate the pace a little bit. So, Scott, what is this construct?
It's a mux.
A mux. How does a mux behave?
A mux selects one of two lines.
Perfect. So this is the logic construct. It's not a magic box of any kind. It's simply a box that produces an output C that's a function of the three inputs A, B, and S. So it's, for the non-computer engineers, it's like a logic gate. It's like an AND gate where you have a bunch of inputs, you produce the output. We're dealing with zeros and ones, so all the inputs are zeros and ones. Here is the definition of the function that it implements. So it produces an output C that's going to be equal to whatever the input A is if the input S is 1. So if we put a 1 here, then whatever A is, either 0 or 1, that's what C is. If we put a 0 for S, then the output C is going to be whatever B is. So it's just a logic gate, and this is a metaphor, but what you can imagine inside is a wire, or a switch rather. The switch swings up when S is 1, or it swings down when S is 0 and connects the 0 or the 1. So it's a very simple construct. So this is exactly what Scott suggested. This is the mix the two buckets together and only keep half. Why?
Because you move the S back and forth really quickly.
In a sense you do, but in terms of the bit streams, what's going to be going on here? SA plus SB? Not quite.
So you're selecting every other bit.
Well, so S is going to be a random bit stream coming in. It's going to be stream of zeros and ones. A is going to be a random bit stream coming in of zeros and ones. B is going to be a random bit stream of zeros and ones. And C is going to be the output. What is the formula, Mackenzie?
Well, because like if you put S and you have an equal number of 0 and 1, then you're taking the equal number from A and equal number from B eventually. So that would be like taking the half from each bucket.
Yeah. Well, so the half part is if this bit stream for S is in fact a random bit stream with value 1/2. So if the zeros and ones flowing into S are equally distributed but random, zeros and ones, then I think this is what everybody was saying. Then you randomly flip between the two, and the result is like dividing the buckets in two. But to step through the formula more precisely, like I did for the AND gate, what is the probability of getting a 1 on the output C? Well, it's the probability of selecting A, so P of S, times the probability of getting a 1 on A, P of A, plus the probability of selecting B, which is 1 minus P of S, times the probability of getting a 1 on B. So the lowercase probability values would be C is equal to SA plus 1 minus S times B. And here, for the computer engineers in the audience, this is ordinary arithmetic. This is just plus, minus, multiply. Now, if S, the probability of getting a 1 versus a 0 on this input, is a half, then we get 1/2 of A plus 1/2 of B. So this implements scaled addition. It implements addition, but we scale each value down and then add them. And that's actually a perfectly valid thing to do with probabilities. So we know how to do multiplication, and we know how to do scaled addition. What I'll show you next is how we implement arbitrary polynomials. So how can we implement a function that's, let's say, 3x cubed plus 1/2 x squared minus 10x plus 12, or something like that. Or where am I going with this? So what type of operations can we do? Polynomial operations. Any ideas? So Chris, I'm picking on you a lot. What are the restrictions? How would you do it? If we know how to do multiplication and addition, then it seems pretty intuitive that we can just do polynomial operations, right? Yeah? But why can't we just implement the polynomial calculation as a series of additions and multiplications?
Sure.
Sure. But what might be the limitations of doing that? Anyone? Scott?
Is it scaled addition?
So that's one problem, that we're limited to use scaled addition. The other problem is that we're dealing with probabilities. So let me put it differently. Now that I've showed you how to do multiplication and addition, suppose you were just beginning this research project. I did this with a PhD student. You're really excited because you've understood how to do multiplication and addition. But now the goal is to generalize this so that you can implement circuits like thermostats or other circuitry to do useful things using this paradigm. What is the immediate stumbling block? That any function that you implement has to map probabilities to probabilities. That's all that you can do. Mapping probabilities to probabilities means that you can only map from real numbers in the range 0 to 1 to real numbers in the range 0 and 1. So we'll have to work with polynomials that map the range 0 to 1, real numbers, to 0 to 1. So I'll show you how to do that. Okay, but let me step through a little bit more of the structure of what we're talking about here, just to get you guys on the same page. Okay, so the scheme that I'm going to describe is one in which we represent numbers as the probability of a given input being 1 versus 0 in a random bit stream. So we're going to represent a number in the range 0 to 1 by such a bit stream. And then, based upon that, we're going to do calculations. So, throughout the lecture and throughout the discussion, I'm going to be talking about bit streams. I'm going to be talking about a sequence of zeros and ones streaming on a wire. Somehow the explanations are easier and intuitive that way. That would be this type of representation. But in fact, when it comes to implementing it, what we'll often use are it's kind of a parallel model, and the parallel model simply means take your head and tilt it sideways. When you tilt it sideways, so now we're going to represent the number as the fraction of ones versus zeros on a bundle of wires. So, and it turns out that the full theory, which is reasonably complex, it applies to both the serial case or the parallel case. You just have to turn your head sideways. Or, stated differently, the serial model, the bit stream model, is one in which things are random in time. So you get a number, but you have to wait quite long until you get it, because you have to get enough zeros and ones to make an estimate of what you need. The bundle model is one that's closer to the model of the caveman currency with buckets. It's where you have a bundle of wires together, and the number is simply represented as the fraction of ones versus zeros in the bundle of wires. And then all the operations I'll describe, we can do them serial in time, or we can do them parallel in terms of wires in the bundle. We just always have to adhere to the same principle, which is to do things randomly. So the numbers we assume are randomly distributed in the stream or randomly distributed in the bundle, and we have to do the operations on it. So let me skip over this because this really deserves a full lecture on it. But how might this be implemented in practice? Well, in several ways. One is we can actually use ordinary digital circuitry. Ordinary digital circuitry where you randomize the inputs, use ordinary AND gates, and operate them that way. But a more compelling way to implement this idea is to use true parallel bundles of wires. And these parallel bundles of wires could be something built, for instance, out of carbon nanotubes, if you guys have heard of this. This is very newfangled technology that instead of representing digital circuitry in terms of silicon and metal connects, we use something like carbon nanowires, which are extremely small and extremely fast and extremely cheap to make in quantities. And they will be the bundles of wires that carry our digital data. And again, I'll defer this until a lecture where I describe it properly. But the point is that when working with a bundle of carbon nanotubes as our wires, we have a lot of them, and they're very small in terms of their diameter. And what goes on is digital. It's either 0 and 1 in terms of voltages, but it's also somewhat random. So this is a particularly good fit for the model where we have lots of very cheap wires that we can connect. Okay. But suspend your questions until I describe that properly. Okay. Okay, so instead, what I'd like to focus on today is a little bit of the mathematics in terms of implementing arbitrary functions. But again, to clarify what's going on, we're going to make a conceptual shift. The shift is when discussing how a circuit is built, instead of describing it in terms of binary values and a circuit that operates on binary values, we're going to discuss a circuit that operates on randomized bit streams or wire bundles. And so we're going to begin to treat the probability value as the value that we compute on. So with such a circuit, and forgive the jargon, combinational, inside it's just logic gates. We're going to make the conceptual shift to view our computation as one in which what comes in are probability values. We have a circuit that operates on them and produces probability values. And so that's going to be our computation. It's a very different way of thinking about a circuit where you encode the numbers by probabilities. So we have bit streams in, bit streams out, or in terms of the parallel bundle system, what we have are bundles of wires in and bundles of wires out. But again, what we're interested in are the fraction of ones versus zeros on each bundle representing a number, and then we produce a circuit that operates on those numbers. And all of our constructs will assume, like this one here, that separate bundles are random and independent. It's going to be critical that if we don't randomize the values, our circuits won't work. Just like in the case of caveman currency, if let's say the black rocks were heavier and they'd all fall to the bottom, it wouldn't work, if you think about it for a moment. Because then, reaching in, the probability of getting a white versus a black rock wouldn't be representative of the fraction of black versus white rocks, and nothing would work. Okay, so everything truly has to be random. All right. So, okay, this is what I described earlier, or perhaps I didn't, in terms of Jason's very good question, which is, all right, well, so you have some sort of scheme where you operate on randomized bit streams, but what do you do with those numbers? Well, suppose that you had analog to digital converters that convert your inputs to this form, and your circuit that does the computation, and then you have digital to analog converters on the output. You could produce an entire system that operates this way effectively. So what I'll try to describe today is how we can do much more than simple multiplication and addition. We can do relatively complex operations, like this is an example that I'll show, which is gamma correction. So can anyone take a guess? What is gamma correction, and when, where would you use it? I need a new victim. Jordan?
Is that like correcting the exposure on like old photographs or something like that, or images?
Yeah, I think that's all about I understand. It's that often in a video display system, you've got pixels and the brightness of the pixels, and gamma correction is something that's done in just about every display where you take the pixel value, and you don't display the pixel value in the data, but what you do is you take the pixel value and you raise it to the power 0.45. That's a typical value. So what does this mean? Well, imagine that the data that you want to display in your video system is given as pixels, an array of pixels, each of which is a number. If it's a grayscale image, between 0 and 255. So each pixel is a number between 0 and 255. You want to take that number and raise it to the power 0.45, and that's what you're going to display. So in other words, we need a computing system that, given an input, which is some number, raises it to the power 0.45. How would you do this in a typical computer system? Any suggestions? What's your name? In the front? Akash. So you were nodding, meaning that perhaps you had some familiarity. How would you build such a system?
I have no idea.
Yeah. So Hassan in the back, how would you build such a system in a regular, in the regular paradigm?
Power of a number?
Uh-huh. So what you might use, I think, is take this mathematical function, express it as a Taylor series expansion, and then compute the Taylor series expansion of it, right? You might do that. And so this would mean in your regular system, you would be doing, to raise something to a power, you'd be doing quite a lot of, for the Taylor series expansion, quite a lot of multiplying and adding. All that multiplying and adding, if you do it the conventional way, requires a lot of gates, because you've got to build your multiplier and your adder. So it means that the circuit that does gamma correction, which sits in your video processing system, consists of a sea of gates, perhaps several thousand, to do addition and multiplication to perform this function. I want to show you a way to do it that's going to require a tiny, tiny fraction of the number of gates by using the caveman paradigm. So it'll take me a little while to get there. But the upshot of where I'm going with this is it really is, in a sense, by making this conceptual shift from a positional system to a system that's, I should, instead of calling it for this course, I'll just call it the caveman system. So the caveman system is one in which, I'll have to convince you of this, but we can do very complicated operations with very simple logic. There was the example of multiplication and addition that we could do with very simple logic. But that'll carry over to much more complicated designs. And so without bragging or boasting about the effectiveness of this method, the reduction of circuitry is on the order of a factor of 100. So if it requires 100 gates to do something the conventional way, like 100 gates to do multiplication, it takes us 1 gate to do it this way. If it requires 1,000 gates the conventional way, it takes us 10. And this is pretty surprising and pretty exciting, I think. But Jason, what is the skepticism in your mind immediately?
Well, I'm going to wonder about speed.
The speed. So, exactly. So why is the speed potentially a huge problem here?
Because if you're doing it serially, you're waiting for data.
And potentially you're waiting for a lot of data. So the limitation of this paradigm is the speed if you've got your head facing this way. What's the limitation if you've got your head facing this way? It's going to be the size of the bundles. So the basic limitation is, by choosing a caveman encoding, which is a fraction of ones versus zeros versus the possessional system, we need a lot of rocks to represent a number relative to what we would with a positional system. How many? Well, if you can represent a number in the range 0 to the power 2 to the n minus 1, which is what you can represent with n bits, to represent the same number, the same range of values, you need an exponentially larger number of bits or wires. Is that clear to everybody? So to represent, so how many bits do we need to represent a number in the range 0 to m in this system? Scott? We need log 2m in binary, positional. In this system, we need m. So basically for this system, let me write this down instead of saying it. Sometimes I get lazy. It's coming on one of the slides. So with, I'll call it binary radix. We can represent, suppose we're given a budget of n bits. So we have n binary digits. In decimal, if I give you 3 decimal digits, you can represent numbers in the range from 0 to 10 to the 3 minus 1, or from 0 to 999. In binary, it's similar. If you're given a budget of n bits, you can represent numbers in the range from 0 to 2 to the n minus 1. With caveman representation, if you're given n bits, you can represent numbers in the range from 0 to n. So it means that given a budget of n bits, the difference is exponential. The difference is between 2 to the power n. Or stated differently, going in the other direction, we can represent a logarithmic number of fewer bits with this representation. So it means that this representation is horribly inefficient in terms of the number of bits that we need to represent numbers in a given range. Or if we're waiting for the serial representation, we have to wait for a lot of bits until we can get the number that we need compared to binary radix. So this, as we've been with students, including Hassan in the back, as we've been developing this paradigm, this is a criticism that we face, that, as Jason said, these circuits might be incredibly slow. We might have to wait for very long bit streams to get the kind of accuracy that we need for the computation. And that's true, but if we can get by with a circuit that's 1% of the size, or we can have a 100x reduction in the number of gates, that might be a price that we're willing to pay. But then there's also the issue of turning our heads sideways. If we turn our heads sideways, then sure, we need a bundle of wires that's exponentially larger to represent a given value. But the trend with newfangled technologies, types of nanotechnologies like carbon nanotubes, is that the number of wires, the density of wires that we can get is often very, very high. And so having a lot of bits is often not the limitation. The limitation is the fact that the circuitry tends to be unreliable, it tends to be random, it tends to be hard to control. As I'll try to explain in a moment, randomness, first of all, is our friend here, because we want everything to be random. So in conventional systems, randomness is your enemy. You know, your zeros and ones being flipped arbitrarily, this is very bad. Here, in a sense, randomness is our friend. We want things to be random. But more importantly, if there are bit flips, if ones randomly change to 0, this method is going to be very resilient in terms of the number of ones and zeros that can flip before there's any degradation. Okay, let me, in the remaining 15 minutes, delve into some of the mathematics of it. So the goal here, and I think that the difficulty in what I'll present here is in the mathematics. So for the non-computer engineering students, you're not really at a disadvantage. I think everybody's going to be scratching their heads a little bit about the mathematics. But that said, I'm going to be talking about logic gates. This is really a topic in how to synthesize the logic gates to build something. And it's a pretty advanced topic. So just bear with me, and if it doesn't make sense, let me re-explain it. So our goal here is going to be to try to produce the contents of this green box, being AND and OR gates, that computes a function. And it's going to be a general function. It's going to be a general synthesis method. So it'll be a circuit that, let's say I've just picked these numbers out of a hat. 0.7 produces 0.616. Or a little bit more precisely, suppose that the input is a number t, like a temperature measurement on a thermostat. The output might be some function of t. So in this case, it might be this polynomial function. It could be that for the Nest thermostat, this is the function that you have to implement. So you turn the heater to this level, which is this polynomial function of the input temperature measurement. And in general, this type of computation is extremely common in computer systems. For, I mentioned video processing, it's very common that you have to implement some sort of polynomial function. But it's also very common in signal processing, in audio processing in general. And that's really, for the time being, and I hope with students like Hassan we'll generalize this, but for the time being, this is what we know how to do. We know how to implement polynomial functions of the input. But what does this mean more precisely? We're here, t is going to be a probability value in this paradigm. So we already have to make the shift that whatever input we have, we're going to transform it to a probability. And the circuit is going to produce a stream of zeros and ones where the probability of the 1 versus a 0 is going to be this polynomial function. So I think you guys are all getting it. But it's really a different shift here because it's a circuit that is doing something randomly. And we're interested in the probability that characterizes that random event. Okay, so the mathematical model, let's generalize this a bit, would be that the input to our circuit consists of Boolean variables. They're all 0 or 1, but they're random and independent. In the previous example, there was a single input t. Here I'm showing that we might have multiple inputs, x1 through xn. But we will still be computing a univariate function. So what do I mean with that? Am I starting to confuse you a little bit? So Chris, what do I mean by a univariate function when we have multiple variables? But tell me, am I confusing you, or are you just waiting for me to say more?
A little both.
A little both. Okay. So here, suppose that each variable assumes a probability that is independent, but is set to the same value t. So what do I mean by that? Suppose that we have multiple input bit streams, x1, x2 through xn. They're each random bit streams going in. But imagine that on each I had a knob, and I could turn the knob to a certain value t. Then the probability of a 1 versus a 0 in that input bit stream, each will be independent, but each will have a probability of a 1 versus a 0 equal to t, if that makes sense. Or here, confusingly enough, I used lowercase x. So the probability of each line being equal to 1 is going to be the lowercase xi. So what does it mean? Well, if I just have an ordinary circuit consisting of logic gates, and I feed in a bit stream, I feed in bit streams, I get a bit stream out. So the bit stream out is going to be some function of the bit streams in. If the output variable is y, I'm going to have the output probability y equal to a function of the input probabilities. So what can you say about that function? Any idea, Jesse? So what kind of function could you get there? Could you get arbitrary function?
Could you get an arbitrary function?
Yeah. So can I implement here hyperbolic tangent? What's your intuition? I know you can't just answer that off the bat.
I would probably say no.
Yeah. So as it turns out, the only functions we can implement. And so it's kind of, this is a profound statement on this paradigm. Regardless of what I put in this green box, regardless of what C of and or and other logic gates I put in, everything that I get out is a polynomial function. So this paradigm, and there's really no way around it, if I compute on probabilities and I do logic operation on probabilities, all I get is a polynomial function of those probabilities. So why did I talk to you about the gamma correction function? Yeah, Jesse.
But again, you did a Taylor series expansion.
Exactly.
Like, say,
And that's exactly what we're going to do. It's not going to be a Taylor series, but it's going to be something like a Taylor series. And that's, in fact, how we can implement something like gamma correction, which is not a polynomial function, raising something to the power of 0.45. But we're going to approximate that as a polynomial. And it's going to be a very good approximation. Okay. All right. Let me skip right over this, because this is the scary math, and show you the circuit instead. It's not scary math at all for you guys, but I know from experience that it can turn people off. And math shouldn't turn us off. It should turn us on. Is that politically incorrect for me to say? Okay. All right. Let me jump right in and show you a circuit. And this is, it's not a complicated circuit, but it's a real circuit. And then together, let's try to characterize what the circuit computes. And then all the math that comes afterwards is just to explain to you how you can take a polynomial and package it in the right form. So this particular circuit computes it. So this is going to be a general circuit that I claim can compute any polynomial function. So what is this circuit? Well, this needs some explaining. Ignore this for the moment. Here, this particular circuit up here is going to be a multiplexer, which is the same construct that I showed you before. So the multiplexer is just an ordinary logic circuit. In this case, based upon the input up here, it's going to select one of these input lines. And here I'm already using quite a bit of circuit notation jargon, as it were. So the select line is not going to be a single line, but since I put that that diagonal line on it, it's going to be a few lines. So in this case, if we have n inputs, how many select lines will we have? I need a new victim here. So yeah, how many select lines will I need if I have n inputs z? Yeah. Log base 2. So in other words, or suppose that I had 8 inputs z0 through z7. Then I would need 3 select lines to select one of those 7. Is that okay? It's just because in binary, if you have 3 select lines, you can specify a number between 0 and 7 in decimal. So up there, we'll have 3 select lines for 8 inputs. That's all this circuit does. And this circuit is just an ordinary logic circuit, meaning that it produces an output that's either 0 or 1, depending upon what the value of the input is here that's selected by those select lines. Okay. So now, the other part of the circuit on top is going to be an adder. What does the circuit do? Well, the circuit is going to take a bunch of inputs, x1 through xn, and is going to produce in binary the sum. So what do I mean by that? Suppose that I had, and it's confusing that I guess I use 0 and n as my indices, but suppose I had numbers 1 through 8 for my inputs, or suppose I had 8 inputs, x1 through x8. Suppose that, and so that would go then to 3 input lines in the select. Because with 8 bits, I can have a number that ranges between 0 and 8. So I guess I would need, would I need 4? Would I need 1 more? Okay, I'm not sure about that. But so here, for the select line produces, encoded in binary, the sum of the number of 1s that I see on the inputs. Does that make sense to everybody? Okay, so what does this whole circuit do? Can anyone now, in just one step, make a leap to the probabilistic argument? It'd be very hard to do. I'll just let you stare at it for a second. Because in fact, what we're going to have is we're going to have bit streams coming in for the x's, bit streams coming in for the z's. And we're going to want to discuss what the probability is of getting a 1 at the output. So Mackenzie, can you begin to sort this out? You're good on your feet.
I'm not sure about this.
Yeah. Okay. Let me just show you the result, and I'll take this up, and I'll, fear not, I'll explain this properly on Friday, what it does. But here's what it's going to do in a sense. Suppose that, so what we're going to do for the inputs, x1 through xn, that go into the adder, we're going to put in multiple independent bit streams that are all turned to the value t. So imagine we've got a dial. We can set that dial to whatever value. We're going to set it to t, but we're going to set it to t for each of the independent bit streams. So if we set it to a half, it means we have random bit streams that all have a probability of a half going in. We're going to add the number of ones that we see in a given slice. So all the bit streams are flowing in. We're going to look at a slice. If we look at a slice, we're going to look at the number of ones that we see. Based upon the number of ones that we see, we're going to select one of these lines coming in. And then for these lines coming in, these are also going to be random bit streams, but these are going to be bit streams that are going to be set to the coefficients. So if we've got a polynomial, multiplying each variable is going to be a coefficient. We're going to set the coefficients to be the input bit streams here. And then we're going to, based upon a little bit of mathematics, package things up appropriately. So up here at the top, I'll just conclude with this. And I hate concluding with this because I've left you all in a state of massive confusion. And I'm not oblivious to that. I'll explain it properly. But can anybody who is even remotely following what I'm saying guess where that formula at the top comes from? It's a Bernoulli distribution of what? Very, very good. Yeah. Perfect. So you guys may recall Pascal's triangle and all that. The number of ways of choosing I out of n objects is the notation n versus I. What is n here and what is I? What am I choosing?
N is the total number of events, iterations.
Yeah. Or the number of ones that I get on the inputs to the adder. Yeah.
I is number of times a particular event took place.
Okay. So rather, I is going to be the number of ones that I get on the inputs to the adder out of a total of n bits. So the point is, how many ways do I have of getting 3 out of 8 inputs? Well, it's going to be n choose 3 ways that I have of getting 3 out of 8 inputs. For each of those, the probability of getting 3 out of 8 inputs to the adder being 1, well, is going to be t, which is in this case the probability 3 over 8, raised to the power 3, because I have to get 3 of those, times the probability of not getting a 1, which is getting a 0, which is going to be 1 minus t, raised to the power of 5 over 8. So that's where this construct is going to come from at the top. We're going to take that construct, and that's going to tell us which select line we select, and we're going to multiply that construct by the coefficient that we get. And this is going to be the form in which we package the polynomial. Right. I'll re-explain that at the beginning of next course. I'll post the slides immediately, and you can take a look at it. This is not going to be representative of the course. I'm not going to be hitting you with these kinds of calculations, but it's a specific construct. Okay.
0 to n minus 1.
So if you walk in, get it home. Hold this all the way to the bottom.